In this video, we will talk about what the price elasticity of demand is. So the question that we're going to be trying to answer is, when we change the price a little bit, how does that affect the demand? Will it change it a lot, or will it change it a little bit? And then what impact does that have on the revenue? So I want to motivate this with an example. So let's say that a company projects that its demand model for hair gel is given by Q of P equals 0.1 times 50,000 minus P to the fourth, where P is the unit price in dollars. Okay, so what I want to do is I want to look at a specific, I'll call this an initial value for my price. So an initial value, okay, for price, and I'm going to say the initial value for price is $5. And when the price is $5, let's figure out what the demand would be, what Q would be. So Q would be 0.1 times 50,000 minus, and now we plug in the 5 for the P, and we'll get 5 to the fourth, and then close that parentheses. And if we work out what this is, this ends up being 4,937.5. Okay, so far we are keeping track of the price, we're keeping track of the demand, and now we could also compute the revenue. So the revenue is what we'd get by multiplying P times Q, the price times the quantity. And if we were to work this out, we end up getting 24,687.5. Or we could say that's 50 cents at the end. All right. Okay, so I'm going to start to organize this into a table. So I'll put a horizontal line here. And what I want to do now is I want to look at what happens if we increase the price by 1%. So just a tiny amount. So if we increase the price by 1%, okay, so let's extend these lines down, and I'll add a horizontal line here to make another row. So if we increase the price by 1%, the new price is going to be $5.05, because 1% of $5 is what we get if you multiply this by 1 over 100, and that's 5 cents. So we'd add 5 cents to $5. Okay, so that's what we get if you increase the price by 1%. And if we now compute the demand, we would plug in this price into the demand function for P. In doing that, we end up getting, this one I'm going to approximate. This is approximately equal to 4,934.9, whoops, sorry, okay, and then there we go, 0.96. So it's an approximation because I'm rounding this to 2 decimal places. And if you multiply this price and this demand together, we get the revenue. Well, this is going to be an approximation as well because Q is an approximation. So this will give us some value. It'll give us $2,921.56. Okay. So the next thing that I want to keep track of in this table, I don't want to go quite that far down, is the percentage change in everything. Okay, so the price, well, that we selected to go up by 1%. So the price went up by 1%. If I want to figure out how much as a percentage did the demand change, I would take the final demand, which is 4,934.96, subtract the initial demand, which was 4,937.5, and divide it by the initial demand, which was 4,937.5. And if we work this out with the calculator and we convert it to a percentage, it ends up being approximately negative 0.05% if I round it to 2 decimal places. Okay, so that's a pretty small amount. So even though the price went up by 1%, the demand dropped by very little, just negative 0.05%. So overall, as a percentage, the price increased more than the demand decreased. So we kind of expect that the revenue is going to go up. So let's just verify that. So let's get the percentage increase. You know what? I think there's an error in one of these numbers. I don't think this should be 29,000. Should be, I think I just miswrote that. This should be 20, oh, this should be 24,921. Okay, so let's figure out the percentage change in revenue. So I do my new revenue, 24921.56, minus the initial, which was 24687.5, and then divided by the initial. So the initial was 24687.5. And using a calculator, this ends up being about 0.95%. So that's my percentage change in the revenue. Okay, so let's summarize our results here. So when increasing the price from $5 to $5.05, which was just a 1% increase, the demand decreased by a smaller percentage. By a smaller percentage, it decreased by negative 0.05%. So when that happens, we say that the demand is inelastic to the increase in price. So that word inelastic just means that it doesn't change much. The demand is not particularly sensitive to changes in price here. It didn't change a whole lot when we increased the price. So as we saw on the table, when the demand is inelastic like this, when it doesn't drop a whole lot when we raise the price, this implies that raising the price will end up increasing the revenue. So when that happens, it's beneficial to raise the price. Okay, so here, when the demand is inelastic, it's beneficial to raise the price, because raising the price will result in the demand not dropping by a whole lot. So overall, that's going to benefit the revenue. It'll increase the revenue. Okay, so let's look at one more example, one more value for P in the same example. So let's say I'm working with the same example, but now let's say my initial price is $11. So if it's $11 and I plug that in and I figure out what my demand is, I'll get 3,535.9. And if I multiply the price and the demand to get the revenue will end up being 38,894.9. All right, and now, just like before, I want to increase the price by 1%. So 1% of $11 is 11 cents. That's what we get if you multiply $11 by 1 over 100. So adding 11 cents to $11, we'll get $11 and 11 cents. And then if we plug this in to figure out your demand, we end up getting 3476.45. And this is an approximation. This is rounded to 2 decimal places. All right. So with this example, let's see if we can let's see if we can estimate whether the revenue will go up or down without actually computing it. Let's see if we can do this just using the percent change in price and the percent change in demand. So price went up by 1%. And demand, if we were to work it out just like we did in the example above, we'll get that this changes by negative 1.68% if I round it to 2 decimal places. So in this question, now when we increase the price from $11 to $11.11, so a 1% increase, the demand decreased by a larger percentage. It decreased by 1.68%. So I'm going to write negative 1.68%. That's how much the demand changed. So when that happens, when the demand drops by a larger percentage than the price increased, then we say the demand is elastic. Elastic means it's very sensitive to changes in price. So when it's elastic, it changes more significantly. So based off of this, even though the price went up, the demand went down by a greater percentage. And based off of that, conceptually, I would expect the revenue to go down. So if we were to check that now, the revenue when we increase the price by 1%, if you multiply this price, the 1111, times its corresponding demand, we end up getting $38,623.38. So that did go down. So, and the change in price, the percentage change, if we were to work it out, just like we did in the table above, will end up being negative 0.69%. Okay, so we did confirm in this table that the revenue does go down. But we were able to predict that change in revenue pretty well using these percent changes in price and demand and thinking about, well, which one changes more? So in this example, in this second example, raising the price from $11 to $11.11, when we raise the price, the revenue decreased. So the revenue decreased. And when that happens, it's not going to be beneficial to raise the price because we'd have a lower revenue. It's going to be beneficial to lower the price. To lower the price. Okay, so when the demand is elastic like this, it's going to be beneficial to lower the price if we want to raise the revenue. Okay, so next I'd like to have some terminology to be able to talk about sort of the comparative difference between percent change in demand and the percent change in price. So I'm going to call that the price elasticity in demand. And what it is it's the percentage decrease in demand divided by the percentage increase in price. Okay. So for the percentage increase in price, the way we figured out that percentage increase was we got the change in the price, and then we divided it by the initial price, which I'll just call P. And then we convert it to a percentage, which we can do by multiplying this by 100, and then that'll give us a percent. And now for the numerator, it's also a percentage change, but it's the percentage that the demand decreases. So I'll measure it as the change in demand divided by the initial demand, which I'll call Q. So just like we did, Q. So very similar to what we did on the denominator. And to make it a percentage, I'll multiply this by 100%. But because I want the percentage decrease, to account for that, I need to stick a negative in front of this. So without that negative sign, if I just get rid of it for a second, the demand, at least when the price rises, so if the price rises, we would expect the demand to go down. So the percentage in this numerator would be a negative value. So with this elasticity, this quantity that we're defining, we'd like it to be a positive number. And to make it a positive number, we want to stick a negative sign in front of this, because that'll change the negative value we had on the numerator to a positive number. And technically, if I go back to our tables, it agrees with what we were sort of saying here if I just modify my notation a little bit. So when we talked about how much the demand decreased, I said negative 0.05%. I technically shouldn't have said the negative in there. I should have just said, oh, how much does it decrease? So it decreased by 0.05%. The fact that I'm saying decreased, I'm using this word decreased, already means it's going down. So I shouldn't put a negative in front of it. That's kind of like doing a double negative. Okay, so similarly, in my second table, it would have been better to say that the demand decreased by just 1.68%. So I can either say that the demand changed by negative 1.68%, or I can say that it decreased by positive 1.68%. Okay, so if we go back up to where we were defining this elasticity, as we just saw on the table, the percentage decrease in demand needs to be a positive number. And when we don't have this negative sign, the numerator right now is going to be a negative value because the demand is dropping. So because we're talking about the percentage decrease, we need to make that negative a positive. So we put another negative in front of it. Okay, there we go. We got that negative. All right, so now if we simplify this, the 100 percentages are going to cancel, and we end up getting negative change in Q over Q on the top. And then dividing by the fraction on the bottom, we multiply by the reciprocal. So times P over change in P. And it's nice if we put the deltas together. So we get negative delta Q over delta P, and then times P over Q. All right, so what I want to do now is I want to draw a graph of just an arbitrary demand function, so some function Q of P. So let's say my function looks something like this. So I got my axes, and let's say my demand graph maybe looks something like this. And then at some price, so this axis is going to be my price axis. The other one's going to be my quantity, or my demand axis. So at some price here, let's say I just plot that on my graph. What delta Q over delta P represents is this represents the change in demand divided by a change in price. That's an average rate of change. We've abbreviated that as AROC for average rate of change. So graphically, that's what we get if we look at another point sort of close by to where price is P. And we connect them with a secant line. If we connect them with a secant line, and I draw these dashed lines, the horizontal dashed line is a change in price, and the vertical dashed line is a change in Q, a change in demand. Okay, so what I'd like to do is, I'd like to get this average rate of change and make it become an instantaneous rate of change. So I'd like to make this an instantaneous rate of change, and we do that by taking a limit. We'd be taking the limit as that change in P goes to 0. So the change in P is kind of like my H, if we remember back in the definition of the derivative. So when we do that, we'll end up taking the limit as the change in P goes to 0 of change in Q over change in P. And when you do that, when you take the limit and you actually let delta P go to 0, you'll get a derivative. It'll be the derivative of Q with respect to the variable P. So in terms of the picture, that would now represent the slope of this tangent line. So for the tangent line, its slope is dq dp, it's that derivative. And for the secant line, its slope was the average rate of change. It was delta q over delta P. So technically, when I said this thing at the top was the price elasticity and demand, it might have been a little bit better to say this was the average price elasticity of demand, because we had this average rate of change in it. And now we've talked about, well, how can we make that an instantaneous rate of change? Okay, so when we do make it an instantaneous rate of change, we get the following definition. This is actually what we'll call the actual instantaneous price elasticity of demand. Okay, so the variable that we'll use to refer to this is, we'll call it E for elasticity. And conceptually what it is it's the percentage rate of decrease of demand per percentage increase in price. And that's the same thing that we saw up here. It's percentage decrease in demand on top, percentage increase in price on the bottom. So basically what we're doing is we're just taking this formula that we had here and changing the delta Q over delta P into this derivative, dQ dP, into the instantaneous rate of change. That's the only thing that's changing about it. And this is going to be our formula for elasticity. Okay, so there are a few other terms that I want to define that we use when talking about elasticity. Okay, so I'm going to organize this into a table. So if my elasticity is greater than 1, then what that means is when we increase the price, the demand is going to drop by a greater percentage. And when that happens, we say the demand is elastic. It is elastic. It is very sensitive to changes in price. Okay. All right. So when that happens, raising the price is going to decrease. It decreases the revenue. And it decreases the revenue, whoops, since Q, which is demand, decreases a lot. Technically, it just decreases more percentage-wise than the price increases. And that's what leads to the revenue overall decreasing. Okay, so in that scenario, is it better to raise or lower the price? Well, if we were to raise the price, that's going to decrease the revenue. So it's better to lower the price. Okay, on the flip side, if my elasticity is less than 1, well, what that means is that the percentage change, that means that the percentage change in demand is smaller than the percentage change in the price. And we say that the demand is inelastic in that case. It is not very sensitive to changes in price. If we change the price, the demand is not going to change by as much in terms of a percentage. Okay, so here, when we raise the price, that increases the revenue. It increases the revenue since Q does not decrease much. As a percentage, it doesn't decrease as much as the price would have increased. Okay, so there it is going to be better to raise the price. If we raise the price, we are going to raise the revenue when our demand is inelastic with respect to price. So the final case is, well, what if E equals 1? If E equals 1, that's called unitary. Unitary, we say the demand is unitary, or sometimes, or the way the book calls it, as the book calls this unit elasticity. Unit elasticity. Oh, and a Y. Elasticity. So in that situation, if we were to change the price a little bit, the percentage change in demand, the percentage that the demand drops, is going to be equal to the percentage that the price would have risen. So raising the price would have no impact on revenue. Okay, and then in that situation, at least instantaneously just changing the price, just a smidge, raising it just a smidge, has no impact on revenue. So is it better to raise or lower the price? Well, that depends on context. Depends on the problem, and I need to know a little bit more specific information to determine whether it would be better to raise it or lower it, or maybe even to keep it the same. All right, so let's look at an example where we start to compute some elasticities. So it's the same example as before, but now we're actually going to start to do some calculus on this. Okay, so we have this demand function, and part A says compute the elasticity when the price is $8. Is the demand elastic, inelastic, or unitary? Okay, so first I need to find my dq dp, because that shows up in the formula for elasticity. So I got to take the derivative of demand with respect to price. So the 0.1 is just a constant. So the constant is multiplying this function, so it just stays there. 0.1 just stays there, and then I multiply that by the derivative of the term in the parentheses. 50,000 is a constant, so its derivative 0, and the derivative of minus p to the fourth is minus 4p cubed. Okay, so multiplying 0.1 times negative 4, we get negative 0.4 p cubed. All right, so remember that E is negative dq dp times p over q. So if we plug into this, we get E equals negative, and then dq dp is negative 0.4 p cubed. Okay, and then this gets multiplied by p over q. But for q, we know we have a formula for q. It was 0.1 times 50,000 minus p to the fourth. So we could simplify this a little bit. The double negative becomes a positive, and then the 0.4 p cubed is going to multiply the numerator of this fraction. So we'll get 0.4 p to the fourth on top. On the bottom, we have 50,000 minus p to the fourth. So now let's plug 8 in. So we want the elasticity when the price is 8. So that gives us 0.4 times 8 to the fourth, all over 50,000. And whoops, I think I forgot to write that 0.1 there. And I need to write this whole thing times the 0.1. So let me not forget that 0.1. 0.1 times 50,000 minus p, which was 8 to the fourth. Okay, so I've rounded this to 3 decimal places, and I got 0.357. So that's part of what the question wanted. It wanted the elasticity, and I know it's 0.357. So this ends up being less than 1. And because it's less than 1, that corresponds to a situation where the demand is inelastic with respect to price. So we would expect that by raising the price, the demand wouldn't drop. It wouldn't drop by as big of a percentage. It would drop by a lower percentage than the price got raised. All right, let's look at part B. That says, should the price be raised or lowered from $8 to increase the revenue? And explain. So in this problem, demand is inelastic with respect to price. So raising the price does not drastically drop or lower the demand. So because of that, the price would be, if we were to raise the price, the percentage increase in price would outweigh the percentage drop in the demand. So overall, because of that, raising the price will increase the revenue. Will increase the revenue. So we should raise the price. We should raise the price. Okay, so understanding this reasoning, so why the demand of being inelastic corresponds to, oh, we want to raise the price to increase the revenue. Really understanding the reasoning is important, for one, because we're trying to really master this content and know why things work and not just what the answer is. And the second reason is, if we understand this logic and how to interpret what it means when demand is inelastic and what it means when the demand is elastic, then there's less for us to memorize because we can just sort of use logic to figure out what the answer should be. And that's nice. Okay, so let's do the next part of this example. This asks, at what price is the demand unitary? So it's unitary when E, the elasticity, equals 1. So let's set it equal to 1. So the elasticity was 0.4 p to the fourth divided by 0.1 times 50,000 minus p to the fourth. So let's set that equal to 1. And now I can multiply both sides by this denominator and get 0.4 p to the fourth on the left. And 0.1 times 50,000 minus p to the fourth on the right. Okay, so one thing that can be helpful in simplifying this further is let's rewrite these decimals as fractions. This is 4/10, and then the 0.1 becomes 1/10. Okay, because this equation, it turns out, is going to be, it's simple enough where I don't need a calculator to solve this. All right, so what I can do next is I'd like to get rid of the fractions. So let's multiply both sides by the denominator, 10, to cancel it out. So multiply both sides by 10. So that cancels this 10, and on the right-hand side, that cancels those 10s. So we end up with 4p to the fourth equals 50,000 minus p to the fourth. So rearranging, we get 5p to the fourth equals 50,000. So dividing by 5, we get p to the fourth equals 10,000. Okay, so now we want to fourth root both sides. So p equals the fourth root of 10,000. And you might be wondering, wait, when I even root both sides, don't I need to put a plus or minus? So you're right. Typically when we even root both sides, we would need to put a plus or minus. In this situation, we don't need a plus or minus since p is a price, and a price can't be negative. That wouldn't make sense in this context. So that's why I don't need to worry about the plus or minus here. And this is actually something I can simplify. Fourth root of 10,000. What number multiplied by itself 4 times equals 10,000? And the answer is it's 10. So that's the fourth root of 10,000. And so this was a price, so it does have units. In this question, they were dollars. Okay, so that's the price at which demand is unitary. This is the price that makes the elasticity be equal to 1. All right, so there's one final part to this example, which is now let's find the maximum revenue. Okay, so one of the ways that we've dealt with finding maxes and mins before was to use a number line. So there's a key observation that I want to make here. So I am going to use a number line, and the point I'm going to put on the number line is I'm actually going to put this value that made elasticity unitary. I'm going to put the 10, and my variable is p, and price can't be negative, so I'll put a bracket at 0 to tell myself, oh, don't worry about plugging in anything to the left of 0. Okay, and what I'm going to keep track of is E, the value of elasticity, on either side of 10. Okay, so if I were to plug in a value that's in between 0 and 10, like let's say 1, and then plug in a value bigger than 10, like 20. So if we were to plug those in to our elasticity function, so here is our elasticity function. If we were to plug them into that, I'm just going to tell you what we end up getting. What type of number do we end up getting? So if we plug in 1, we end up getting a value that's less than 1. And when we plug in 20, we end up getting a value that is greater than 1. Okay, so what does that mean? So when E is less than 1, that means this is inelastic. In other words, when we raise the price by a small percentage, the demand would drop by a smaller percentage. In other words, it's not very sensitive to changes in price. It is inelastic. So in this situation, raising the price increases revenue because overall, raising the price, that percentage outweighs the drop in demand. And on the flip side, when the elasticity is greater than 1, we say that the demand is elastic. So it is elastic. So that means when we increase the price by some percentage, the demand drops by a larger percentage. It is very sensitive to changes in price. So in that situation, raising the price decreases the revenue. It decreases R. Okay, so if we were to draw a graph at this point, so I'm going to try my best to line up the values here with the number line. So I'm going to try my best to line up where 10 is. Okay, let me just erase those guidelines that I drew. Okay, so if this is my price axis and this is my revenue axis, so when price is 10, we're going to have some revenue. And what we know based off this number line, to the left of 10, our demand is inelastic. So if we raise the price, we should increase the revenue. So that graph is going to look something like this. Raise the price, raises the revenue. And on the right side of 10, raising the price decreases the revenue. So that should look something like this. And if that's what my graph looks like, I know what we have here. We have a max. All right, so we can say that the max revenue occurs when the price is $10, since, based off the graph, revenue is increasing. I got to justify why in words. Revenue is increasing for all values of P that are less than 10, and it's decreasing for all values of P that are greater than 10. So if this type of justification looks familiar, that's good, it should. We did something similar to this in optimization questions when we used a number line to get local mins and local maxes, but in optimization problems, we needed to actually justify why those local extreme points were absolute mins and absolute maxes. And this sentence helps us do that. Okay, so we are ready to write down our maximum revenue. So our maximum revenue, well, revenue is P times Q. So this is P times, and Q was 0.1 times 50,000 minus P to the third. Okay, so if we plug in everything now, the price is 10. That's the price that'll maximize the revenue. And then 0.1 becomes 1 over 10. And then we have 50,000 minus P cubed, so that's going to be 10 cubed. Okay, so the 10 and the 1/10 cancel. And whoops, I wrote cubed here, but this should be a fourth power. Let's fix that. So that should be P to the fourth. This one also should have been to the fourth. Whoops. 10 to the fourth is 10,000. So 50,000 minus 10,000, that gives us 40,000. And that's our maximum revenue.